Hello everyone, welcome to the first tutorial of signals and systems. So we start with the first question that says that let xt be a signal of the form cos omega x t plus tau x plus theta x. That means here this omega x is the angular frequency, right, in radians per second. T is the variable time. Tau x must be some sort of delay in time, right? And theta x is the initial phase difference. Now, if we open up this bracket and rewrite this expression, we could say that this is equal to cos omega xt plus omega x tau x plus theta x. Now, in terms of angular frequency and phase, we know that this whole argument needs to be an angle, right? We know already that omega x, this frequency, has got nothing to do with this phase, right? These are independent parameters. So the first question requires us to determine the frequency in hertz and period of xt for each of the following case. So we only need to look at omega x because actually frequency and time period, they have got nothing to do with these terms. Okay, what else do we know? We know that frequency is equal to omega upon 2 pi. Frequency in hertz is equal to omega upon 2 pi, where omega is in radians per second, right? And we also know that time period is 1 upon f. This is in seconds. So for the first case, very simply, we could say f is pi by 3 upon 2 pi. That means 1 by 6 hertz, and therefore time period would be 6 seconds. It's very important that you write the units correctly, and you do write the units for each answer. Right? For the second case, f is 3 pi by 4 upon 2 pi, which is equal to pi and pi gets cancelled. This is 3 by 8 hertz, and therefore time is 8 by 3 seconds. And for the third case, f is equal to 3 by 4 divided by 2 pi, which is 3 by 8 pi hertz, and as a result time is 8 pi by 3 seconds. So in this part B, we have two signals xt and yt, and to start with, let me do a quick correction. This yt, now in this part B of this question, we've got two signals. Xt is same as before, and yt is again a sinusoid. Let me do a quick correction. This would be cos of omega yt plus tau y plus theta y, right? We need to determine for which of the following combinations, means which of these following combinations would xt and yt be identical to each other for all t. By identical, we mean that for every value of t, we mean that value of x of t and value of y of t should be same. Okay? So for two sinusoids to be equal, let me again write it as for x of t to be equal to y of t, right? That means cos omega x t plus omega x tau x plus theta x. For this to be equal to cos of omega yt plus omega y tau y plus some theta y. For these to be equal, what is important? It is important that their frequencies need to be equal, because for two sinusoids to be equal in any way, their frequencies have to match, right? That means for them to be equal, omega x has to be equal to omega y. And it may even happen that even if two frequencies are equal, the signals are still not identical. Why? Because there is a phase difference between the two. That means for them to be identical, these phases should also be the same. And because these are angles, we can say that phases are same even if they differ by an amount of 2 pi. That means omega x tau x plus theta x should be omega y tau y plus theta y, and it's okay even if they differ by an amount of 2 pi k, where k is an integer, right? So these are the two conditions that we need to check before saying whether these values of omega x and omega y will make xt and yt identical. So let's start with the first part. The first thing we've got to check is, are the frequencies same? So omega x and omega y, yes, the frequencies are same. We now do the second check. Omega x tau x, product of these two, that means pi by 3 into 0, plus theta x, that means 2 pi. So you've got 2 pi on the left hand side. Let's see what's there on the right hand side. Omega y tau y, product of these two, pi by 3, plus theta y, that means minus pi by 3, plus 2 pi k. We notice that these cancel out, and for k equal to 1, this is actually equal. Left hand side is equal to right hand side. That means this condition is correct, right? For the second case, omega x is 3 pi by 4, omega y is 11 pi by 4. The frequencies are not same. There is no need to check any further. This cannot guarantee that xt and yt will be equal. Third case, omega x is 3 pi by 4, omega y is 3 pi by 4. So frequencies are same. We go to the second check. Omega x tau x, 3 by 4 into 1 by 2, plus theta x, 1 by 4. Let's see if it's equal to 3 by 4 times 1 plus 3 by 8 plus 2 pi k. We notice that this is 3 by 8 plus 1 by 4. This is 3 by 4 plus 3 by 8. These are not equal even for k equal to 0. Right? For k equal to 1 and other integers, it's obviously not possible. So the third case is also, it's a no. All right. If we went and made this sin x, right? If this was sin x, then the only difference that would come into picture is that for these phases to be equal, instead of 2 pi k, you would also have a term of pi by 2 plus minus, or this whole term, and at the end you could say plus minus pi by 2. Okay? And then you would do the check. The next question requires us to sketch certain signals, right? So it's a problem of sketching time scaled or time translated versions of discrete time signals. So the signal is already given to us xn. So we need to sketch these three signals. If this is xn, what is xn minus 2? So now you already know that if a signal is being translated by a negative number, that means there is a delay, right? There's a delay. So in that case, the signal is moved to the right hand side of the axis by that much amount. So I'll start with solution of A, 1. So x of n minus 2 would be something like this. Let me draw the axis. X of n minus 2 means the whole signal xn will be shifted to the right hand side by 2 units. That means whatever was at 0 now goes to 2. What was at 0? A value of 1, that goes now to 2, right? Whatever was at minus 2 now goes to 0. What was at minus 2? 0 was at minus 2. No signal, right? Minus 1 would go to minus 1 plus 2 plus 1. That means this would have translated to this point. Okay. What else? What would be the extreme? 3 would have gone to 5. Okay. So here everything remains the same. 4, the value of 4 was 1 by 2. That would have gone to 6. So these are all 1 and this is 1 by 2. And beyond 6, the value would be 0. Right? Because from 5 onwards, the value of the signal is 0. So it's important to draw the axis, and this is what x of n minus 2 should look like. Okay, this is first part. Now the second part is x of 4 minus n. Now, this is where it's important that you keep in mind the precedence rule. If you remember, if any xt, so right now I'm talking in terms of continuous domain, the same holds for discrete as well. If there is some signal xt and you are asked to sketch x of some at plus b, right? That means a is the scaling factor and b is the translation factor or shifting factor, means the amount by which the signal is shifted. In that case, how do you proceed with these operations? Because there are two operations involved, both scaling and shifting. So in that case, always remember that you do shifting first and then you do okay. Now you would be wondering why we cannot do scaling first and then do shifting. Now when you are doing x of 80 first, right? Suppose you've done scaling, and after scaling you get the signal x of 80. Now when you shift this by b, what you are essentially doing is you're doing x of a t plus b, right? That means x of at plus ab, but this is not what was required. This is not what the question demanded. The question demanded translation by x of at plus b, right? So you are unknowingly, unintentionally, but incorrectly multiplying a while you are shifting, right? So it's okay. There is no hard and fast uh, uh, requirement that you have to absolutely do shifting first. If you decide to do scaling first, however, it's very important that you do shifting not by b but by b by a. Okay? Because in that case, it would mean the same thing. So if you are doing scaling first, make sure you're doing scaling by a and then you do shifting by b by a and not b. All right, so this is what is called the precedence rule. Now, why did I mention this here? Because x of 4 minus n is of the form x of minus n plus 4. So this is like saying x of a n plus b, where a is equal to minus 1 and b is equal to 4, right? When the scaling factor is minus 1, this is also known as reflection. So it's a special case of scaling, which is reflection. Now, what should we do? We should first do a translation, that is shifting by an amount of 4, and then do scaling by minus 1, that is reflection. Okay, so let me draw it. Okay, so minus 1, 2, 3, it had values all 1. So now if I want to first shift this, remember that I'm shifting not by minus 4 but by plus 4. That means I need to shift this whole signal to the left side by 4 units. That means whatever was at 0 should go to minus 4. Whatever was at 4 should come to 0. Okay, so I'm going to start from the right side, and whatever was at 4, that is the value 1 by 2, signal value 1 by 2, keeping it here, right? And everything else we are moving. So there were 4 or 5 samples of value 1, right? What is this right now? This is x of n plus 4. Okay. Now to sketch n of minus n plus 4, what you've got to do is simply reflect this whole signal about 0, right? As if there was a mirror here. So I'm going to draw this with red. So 0 remains at 0, right? And rest everything is flipped. These are all values. This is 1 by 2 and this is 1. And the one in red is actually minus n plus 4, x of minus n plus 4. Okay, so what I would suggest is that in exam, you could draw these intermediate outputs, the one that I have drawn in blue here, this you could have drawn with a pencil. And this final step is something which should be very clearly visible, right? Or you could draw it in a separate step. I've superimposed it on the same graph, but what is important is that your solution, what is the final answer? That is x of n minus 4. This should be clearly visible. Okay, so in some other color. Do not use red color in your exam. You can use black or blue, and you have pencil, so gray. So 3 options are there. Let's also check if this would have worked. The other way around would have worked. So if we had done scaling first, that means if I said that let us write this as x of minus of n minus 4, right? That means scaling first by a factor of minus 1 and then shifting, but then shifting cannot be done by a factor 4, it would have to be done by a factor b by a, right? So b upon minus 1, so minus 4. What would have happened in that case? Scaling first by minus 1 means, I'm going to draw it directly on the signal. So scaling by minus 1 means you just reflect this about this axis, right? So it becomes something like this. These 3 will go this side, so they have come here. 4 would go, 3 would go to minus 3, okay, and 4 would go to minus 4. So this is how reflection, or in this case scaling, has happened. So the first step you've done is scaling, but now instead of moving it by 4, you would move it by minus 4. That means you would move it to the right side by 4 units, right? And let me draw this with blue now. So this becomes, so 1 should go to 5, and what was at minus 4 should now come to 0. So 1 by 2 has come here. 1, 2, 3, 4, and 5. These are values 1. This is value half. Is this the same that we got in the previous case? Yes. Starts from 0 up to 5, starts from 0 up to 5, right? So this is important to understand when you have a compound kind of an operation where scaling and translation both are to be done together, of the form x of at plus b, or in terms of discrete time signal, say x of an plus b. The third part requires you to sketch x of 2n, x of 2n. Now we also know that when we talk in terms of x of an, there is no translation, right? So b is equal to 0. Now if a was a number greater than 1, this means that this kind of an operation is going to create compression along time axis, right, or sample axis. If a is less than 1, this is going to create dilation or expansion. Now, how does this compression or dilation look like in signal? So just giving you a quick recap, just for example, if we had a signal xt, say its value was non-zero between minus t and plus t, if this is how your signal looked like, then if we asked you to sketch x of 2t, meaning the scaling factor greater than 1, which should cause compression, right? This means what? That x of 2t will have the same shape, but now the range that it occupies will be half of that of previous signal. So instead of minus t, it starts from minus t by 2 and goes up to t plus t by 2. This is how x of 2t looks like. Similarly, if we said sketch x of t by 2, so it should cause dilation because its value is less than 1. In that case, if this is t, the signal is just, shape remains the same, the signal is just expanded. And now the signal looks something like this. Now see that the value, the amplitude remains the same, right? The shape remains the same and the extremity values remain the same. It is just along the time axis that there is a compression or expansion. So this signal is x of t by 2. Just an example where a equal to 2 or a equal to half. What happens in that case? Now keeping that in mind, here the question requires that a is equal to 2, and for the given xn we need to sketch x of 2n. So what does this mean? X of 2n means a compressed version of xn. So if I started calling xn as a new signal, say yn, right? So what does that mean? That y0 would be what? X of 0, n equal to 0. So x of 2 times 0 is x0. All right, that remains the same. What would be at n equal to 1 for this new signal? X of 2 into 1, right? So x of 2 actually goes to n equal to 1. What would be at y3? X of 6. Whatever was at x of 6 now goes to y3. Right? So there is a compression of sorts. You notice that x of 1 doesn't feature anywhere, x of 3 doesn't feature anywhere. That means literally all the odd terms are disappearing, right? So how would this signal look like? This is how xn looks like. Now x0 remains at 0 very well. Its value is 1. Remember that we are trying to sketch x of 2n. x2 now goes to position 1. So what was at x2? This was at x2. Okay. What comes at position 2? X of 4 comes at position 2, right? What was at x of 4? 1 by 2. Okay. What goes to minus 1? What should have been, whatever was at x of minus 2 would actually come to x of minus 1, right? Because x of 2n means n equal to minus 1 means x of minus 2. So whatever was at minus 2, that is 0 here, that should go to minus 1. Okay. Rest everything is already 0. So this is how your x of 2n looks like. In a sense, what has happened is this whole signal has been compressed, right? Keeping the reference at n equal to 0, keeping this as reference, the full thing has been compressed by factor of 2. So because of that, these alternate samples, they have disappeared, right? Only multiples of 2 have remained. All right. Now, the last part of this question asks, what difficulty arises when we try to define a signal as x of n by 2, right? So remember what we just talked about, scaling factor being less than 1, it should cause expansion, right? Now, when we try to sketch n by 2, what are we saying? To sketch x of n by 2. So let me again call this as a new signal yn, which is equal to x of n by 2, right? So what would be the value of y0? Plugging in n equal to 0, it will be x0 as well. What would be y1? Plugging in n equal to 1, x of half will actually need to go at y equal to 1. But we don't have an x half because we know that xn is a discrete time signal where n can only take integer values, right? So from the original signal, you do not have a x half with you. Right? So you do not have anything to plug in at yn. It is undefined. However, if you go ahead, what do you plug in at y2? X of 2 by 2, that means x1. Great, you have this value. What do you plug at y3? X of 3 by 2. Again, since this is not an integer, you don't have this value. So y3 is undefined. So if you notice, only factors of a times n are defined, right? A being 1 by 2 here. So wherever n by n into a, wherever a into n, that means half into n, that is an integer, only those values are defined. Other values are undefined. So if I was looking at sketching this kind of a signal, right? So x, the same thing happens in the negative side as well, right? So y of minus 1 is what? X of minus half, which doesn't exist. But what is y of minus 2? X of minus 2 by 2, that is x of minus 1. So this we have, right? So if I was trying to sketch this kind of a signal, what would happen? Y0 is x0, all right. Y1 we don't have, okay, so I'm going to leave it. Y2, this is 1. Y2 is what? X1, which is this, okay. Again, n equal to 3, I don't have any value to plug in there. Y4 is same as x2. Y6 is same as x3, okay, and this 4 would have gone to 8. So 8, and nothing to put at minus 1, but at minus 2 you would have put the same value which was at x of minus 1. So you notice that x of n by 2, right now this is not complete, remember, because we didn't have anything to plug in between. So a standard practice is to just put zeros in the undefined value. So you insert 0 and you have basically scaled up your discrete time signal. Okay. It is also common to use interpolation to kind of predict the value of this x half or x3 by 2, which was actually non-existent. You could use interpolation to predict these values, and interpolation will be discussed in a later stage, right, when we talk about sampling. But this is a major difficulty because there are certain signals. The question asked you what is the difficulty, right? When we try to sketch this, there are certain signals only when a times n, when this is an integer, only those values are available. Other values for other values of n, they are not defined, and this is the difficulty. But it can be fixed by putting zeros in the signal, and this or using interpolation to predict these values, to interpolate these values which are missing and undefined. And this is what is called a upsampled signal, right? You've increased the number of samples. Earlier you had just minus 1 to 4, you had just 6 samples in your set. Now you've got 12 samples in your set. Moving on to the next question. For each of these following signals, we need to determine whether the signal is odd, even, or neither odd nor even, right? So what are the conditions? Let us write them down. Just for a quick recap, for an even signal, you need that x of t should be equal to x of minus t. That means the signal should be a perfect reflection about the vertical axis. For a signal to be odd, you need that x of minus t should be equal to minus x of t. Means what? That if you've got some value on left hand side means on the left hand side of the t equal to 0 axis, what you have on the right hand side should be a vertical reflection of that signal, right? That is what is the meaning of minus xt. So rule is pretty simple. So in the first signal, it is very easily visible that this is an even signal, right? Because for every value of minus x of minus t, you have the same value at x of t. Part B is neither odd nor even, right? Because neither of these conditions are true. Part C, all right, you notice that this side and this side are perfect reflection of each other. Notice one more thing, that for practical signals it's also important that if the signal has to be odd, then at t equal to 0 its value needs to be 0, otherwise it won't be a perfect reflection, right? So this is clearly odd. Let us look at D. Now, just looking at it, it gives the impression that it is an odd signal, but if you look at it closely, the plane of reflection that you need to consider, you notice that this is the plane of reflection, right? So it is not really perfectly reflecting. These three samples are not getting reflected here. X of minus 3 is not equal to minus of x3. So this is neither odd nor even. This signal is even, no doubt. This signal x of minus 1 is same as minus of x1, all right. X of minus 2, which is minus 1, is same as minus of minus 1, that means this value. So yes, this is clearly odd. All right, we've now moved to question 4. It says that in this problem, we would explore several properties of odd and even signals, right? So the first part says that show that if xn is an odd signal, in that case, summation of xn over minus infinity to plus infinity is 0. That means if xn is odd, what does this mean? That x of minus n is equal to minus xn. Now, knowing this, can we write the summation xn for n from minus infinity to plus infinity? Can we break this into two summations? Say n from minus infinity to minus 1, then x0, and then another summation n equal to 1 to infinity xn, right? This first term, if you look at this, if I flip the limits, can I say that this is same as saying that n equal to 1 to infinity x of minus n? Rather, what we are doing is we are saying let minus n equal to some variable m, and then we are plugging it here, right? So it's a summation from n equal to 1 to infinity x of minus n plus whatever was at 0 plus this term. Now, because xn is a odd signal, right? Xn is odd. That is why we can say that this term is nothing but minus summation x of n from 1 to infinity, right? So this and this cancel each other out. X0 has to be 0. It has got no other option because it's an odd signal, right? And this gives us final output as 0. Okay, so this is how you prove the first part. Now moving on to the second part, it says show that if x1n is an odd signal and x2n is an even signal, then the product of the two is an odd signal. So, okay, let us start. What is given? So this was part A. Okay, going to part B. What is known is that x1n, what does the question say? x1n is odd. Okay, which means x1 of minus n is equal to minus x1n. Okay, and x2 is even, that means x2 of minus n is equal to x2 of n. We need to show that if there was a signal, say yn, which is a product of x1 and x2, this signal is odd, right? That is what the question requires us to prove. Now, if yn was an odd signal, then y of minus n should be equal to minus y of n, right? So let's just see if that works. So y of minus n would be what? Wherever there is n, you need to replace it with minus n. That means x1 of minus n and x2 of minus n. Now, because x1 is odd, this is nothing but x1n, and because x2 is even, this is nothing but x2n, right? Which is nothing but minus of yn, because this is what yn was, and there is just a negative sign here. So, hence proved. Moving on, part 3 says, let xn be an arbitrary signal with even and odd parts denoted by some xen and xon respectively, right? We need to show that if xn square was summed up from minus infinity to plus infinity, this is simply equal to xe square summed up from the whole range plus x odd the whole square summed up over the whole range. So let's just see what that means. Okay, we know that xn can be written as sum of two functions, one of which is the even version and one of which is the odd version, right? Now, let us start with what it wants us to prove. So let's start with LHS. So summation of xn, the whole square, minus infinity to plus infinity. Let's plug in this expression here. So this becomes, right? Let's open this bracket, a plus b the whole square, right? Limits are all from minus infinity to plus infinity. I'm not writing it again here. Now, let's focus on this term for a second. We notice that this is a product of an even and an odd function. And now just in the previous part, we have shown that the product of an even and an odd function is an odd function, right? And before that, we have shown that if a signal, in part A, we've shown that if a signal is odd, then the summation of the signal from minus infinity to plus infinity is 0. That is what we just showed in first part, right here. So with the findings of both part 1 and part A and part B, we can say that this term would be equal to 0, and therefore summation of xn the whole square is same as summation xe square n and x odd square n, right? N varying from minus infinity to plus infinity. Now moving to part D. Part D says that these subparts A through C were in terms of discrete time signal, but these properties are also valid for continuous time. And to demonstrate that, we need to show that the same property that we just proved, part C, is also true for a continuous time signal. Okay, so the question says that we have a continuous time signal now, xt. And just like for a discrete time signal, we can represent a continuous time signal also in terms of an even signal and an odd signal. Okay, you know how to find these individual signals, right? Given the signal, it will be xt plus x of minus t upon 2, and odd part would be xt minus x of minus t upon 2. So I'm not going into that, but what was asked in the question, let us do that. So question says that we need to do the same summation, but in terms of integration. So integration minus infinity to plus infinity, x square t dt. This is what we need to find, right? And we have to show that this is actually integration x e t square dt plus x odd t square dt. So let's plug in the value of xt here, x e t. Now the same logic, product of an even and an odd signal. Is it true for continuous time as well? Let us quickly see. Let us just call it some yt. Then if you try to write minus yt, you would have got xe of minus t, xo of minus t. But because it's odd signal, so xo of minus t is x of minus t, minus of xt, sorry, right? And xe of minus t, because xe is an even signal, xe of minus t is same as xt, which is minus of yt. This shows us that yt, which is a product of these two signals, is an odd signal, right? And also, if you were to find integration of an odd signal from minus infinity to plus infinity, right? You could break this up and say minus infinity to 0 yt dt plus 0 to infinity yt dt. Let this be, say, 0 minus and 0 plus to infinity, and whatever is the value at y0. Right, and because it's odd signal, these two would cancel each other out and you would get 0. So the logic remains the same, and you can show that since this is equal to 0, LHS is equal to. Alright, moving to question number 5, part A. It says that let xt and yt be periodic signals with fundamental periods t1 and t2. That means x1 and xt and yt are periodic signals. So xt has a period, let me place it here. Now xt has a period t1, that means xt is same as xt plus t1, right? Yt has a period t2, that means yt should be same as yt plus t2. Now if xt is xt plus t1, this is for one period, right? This t1 is one period. Now, would this not be true for a integral number of such periods? So, for example, if I was to write x of t plus m times t1, right, where m is a positive integer, this is still going to be true. Similarly, you could say yt is same as y of t plus, say, n times t2, right? Where n, instead of using n, let us use some other variable. Let us use k, okay? So that you do not mix up the discrete time argument n, right? So t plus k t2, where k is also a positive integer. Now we have to find under what condition is the sum xt plus yt periodic, right? And if it is periodic, what is the fundamental period of this periodic signal? So let us define a new signal, say zt, and call it xt plus yt. We need to find the condition where zt is periodic. Now for zt to be periodic, what do you need? Let us say it's periodic with period t, right? T1, T2 were for x and y, t is for z. So in that case, if zt is to be periodic with the period t, then z of t needs to be equal to z t plus t, correct? Now, what is zt? This is zt. And what is xt? Xt is same as, and what is yt? Yt is same as yt plus kt2. So let me just plug in on the left hand side this plus this. So we are going to write xt plus mt1 plus y of t plus kt2. This is left hand side. This is zt. This should be equal to zt plus capital T, right? And what would be zt plus capital T? If this is zt, right, then what is zt plus capital T? Just replace t with t plus capital T everywhere. That means x of t plus capital T plus y of t plus capital T, right? So instead of zt plus capital T, I could just write this. Now, from this expression, what we infer is that mt1 has also got to be equal to t. kt2 is also supposed to be equal to t. Only then this equation is going to be valid, right? So we can say that mt1 is equal to kt2, which is equal to t. In other words, t1 by t2 is equal to some k by m, right? And remember, we started with uh, the condition that m and k both are positive integers. That means this is going to be a rational number, this ratio. Only if the ratio of the two periods of the signals that are being added, only if the ratio of their respective periods is a rational number, only then will their sum be a periodic signal. And what would then be the period? It could be m times t1, or it could be k times t2. So you need to first find the ratio t1 upon t2, and if it is of the form k upon m, bring it to the form k by m, check if it's rational, and then based on the value of k and m that you obtain, the minimum values of k and m after cancelling out, whatever you get, m times t1, k times t2, both would give you the same thing, and this is what would be the period of xt plus yt. Moving to part B. One very interesting thing about this particular part is that the moment you arrive at this relationship, right, in discrete time, how does that look like? M times n1 is equal to some k times n2, and this should be equal to the actual period n, right? And then you would say n1 upon n2 is equal to k by m. Now notice that n1 and n2, these are what? These are periods of discrete time signals. They are already integers, they cannot be anything else, right? That means there is no way that this ratio n1 upon n2 is not a rational number. It is not of the form k by m, right? It is just not possible, because n1 and n2 are periods of discrete time signals. They have to be integers, which means that this whole exercise is kind of futile, in the sense that the conclusion is that no matter what, as the question asks, under what condition is the sum of xn plus yn periodic, the sum of xn plus yn is always periodic if xn and yn both were individually periodic, right? And what would be the period in that case? The period would simply be, if I was to write it in the ratio, you could say that this is m times n1, or some k times n2. You could just write the ratio of n1 upon n2 in the form of k by m, or you could also say that n is simply the LCM of n1 and n2, right? Lowest common multiple. So this is a major difference between the periodic nature of summation of two signals when they are continuous time and when they are discrete time. All right. Continuous time signals will, if there are two periodic continuous time signals, their summation will be periodic only if the ratio of their individual periods is a rational number, right? It's of the form k by n. But the same case of discrete time signals, if there are two discrete time signals xn and yn having individual periods n1 and n2, right? Their summation is always periodic. There's nothing to check there. Moving on to question number 5c, it says consider the signals xt and yt and show that zt, which is a product of these two signals, is periodic, number one. And we need to write this product as a linear combination of harmonically related complex exponentials. Now, what is the meaning of harmonically related complex exponentials? Before that, what is the meaning of a complex exponential? When you write a signal xt, which is of the form e to the power j omega naught t, right? This is a polar representation of a phasor. What is a phasor? A phasor is a rotating vector, and by Euler's relationship, you could have written that this is cos of omega naught t plus j sine omega naught t. Now, you will study this in a little more detail when you study Fourier series representation. But I understand that this question is basically trying to lay the groundwork for you to understand Fourier series. Okay? So let us start in a very simple way. One thing is that the question requires us to write zt, which is a product of these two signals, as a linear combination of harmonically related complex exponentials. So I just defined what is a complex exponential for you, right? Now, this is a complex exponential of frequency omega naught. If there was a complex exponential of the form cos 2 omega naught t plus j sine 2 omega naught t, this would have been what? E to the power j 2 omega naught t. That means a complex exponential of double the frequency. So it's a harmonic, it's a second harmonic of omega naught, right? Similarly, you could have had e to the power j k omega naught t, cos of k omega naught t plus j sine k omega naught t. So this would have been what? This would have been the kth harmonic of omega naught. Okay? Because what is the kth harmonic of omega naught? K omega naught, right? K times that frequency, that is the kth harmonic. Now, what is meant by linear combination of harmonically related complex exponential? The question requires us to write zt in the form of a linear summation of a some coefficient times e to the power j k omega naught t, right? So this is like, let k be from minus infinity to plus infinity. So this is like saying c1 e to the power j omega naught t plus c2 e to the power j 2 omega naught t plus some c3, some other linear weight, times e to the power j 3 omega naught t, and so on. So this is what the question requires us to do. Okay, and when you study Fourier series, you will understand what this means. But for now, I'm going to erase this and just follow what is asked in the question, right? So the question is giving us two signals, xt and yt. xt, I'm going to write both xt and yt in terms of complex exponentials because it would be easier than to find a product. So xt cos 2 pi by 3t. How can I write this? I can write cos 2 pi by 3t as what? E to the power j 2 pi by 3t minus e to the power minus j 2 pi by 3t, sorry, plus divided by 2, just this term. And then I could write the second term twice of, how can I write this term? Could say e to the power j 16 pi by 3t minus e to the power minus j 16 pi by 3t divided by 2j. This is coming from Euler's relationship. I hope I don't have to write this. Okay, I'll write it in case you have forgotten. So we know that e to the power j theta is cos theta plus j sine theta, right? So we could always write cos theta e to the power minus j theta would be what? Cos theta, because cos of minus theta is cos theta, plus j of sine minus theta, which is minus sine theta. So minus j sine theta. So if I was to write, so these are two linear equations in terms of cos theta and sine theta. So we could rearrange always and write and find that cos theta is e to the power j theta plus e to the power minus j theta by 2, and sine theta is e to the power j theta minus e to the power minus j theta divided by 2j. Okay, that's how I wrote this expression. Now let us write yt also in complex exponential. Sine pi t, that means e to the power j pi t minus e to the power minus j pi t divided by 2j. Zt, which is the product of xt and yt. So let us leave this 1 upon 2j outside. E to the power j pi t minus e to the power minus j pi t. Right, let's open this bracket. Okay. Now we notice that there are certain similarities here. Also notice j pi by 3, j minus pi by 3, right? So this and this term seem to be from the same family. Then you notice 19. So this term and this term, right? And then you notice this term and this term to be from the same family. Like it's of the form e to the power j theta plus e to the power minus j theta form, right? Okay, so what's very important to notice here is that this term pi by 3t, right, j pi by 3t, this remains kind of constant throughout all these terms. What keeps on changing? The factor with which it is being multiplied, right? So the first one, this term, this is like saying 1 by 2 e to the power j 5 times pi by 3t, right? This one is 1 times pi by 3t. This is 19 times pi by 3t. This is 13 times pi by 3t, and so on. So you notice that each of these is a complex exponential, which is a periodic signal by default, right? By definition, it's a periodic signal. It's a complex exponential of one frequency. What you notice is that this whole signal xt is simply a summation of harmonics, right? Harmonics of pi by 3, or rather I should say e to the power j pi by 3t. This whole signal is a summation of certain harmonics, fifth harmonic, 19th, 13th, and so on. Right? We just shown earlier that for a summation of periodic signals to be periodic, you need that the ratio of those time periods, this needs to be a rational number. That means it needs to be of the form k by m. Right? Now, obviously, if first signal is of t1 and the second signal is say 2t1, right, or half t1, obviously k1 k upon m is going to be a rational number. So the moment you are saying that there are harmonically related sinusoids, harmonics of pi by 3 are there, obviously the ratio of their time periods is going to be a rational number. So we have shown that this signal xt, this signal zt, which was a product of xt and yt, this is nothing but a summation of harmonics of e to the power j pi by 3t. And because these are harmonics being added on top of each other, it is still going to be periodic. And what is the lowest common period of these signals? Pi by 3 radians per second. And if omega naught is pi by 3, then what will be the period? 2 pi by omega naught. So 2 pi by pi by 3, which is equal to 6 seconds. Okay. This is one way of showing this, because these were harmonically related, and the moment you have harmonically related complex exponentials, obviously their summation is going to be periodic, because the meaning of harmonic itself is that, say if I had a signal of frequency omega naught, right, its kth harmonic has a frequency k omega naught. If omega naught was the fundamental frequency, in time it had a time period of t naught, then what will k omega naught, this signal's time period be? It will be t naught by k. That is why harmonically related sinusoids, when you add them linearly, so just multiplying with some weights, like here the weights are 1 upon 2j, 1 by 2. These weights are immaterial to the fact that these are sinusoids, these are complex exponentials, and because they are harmonically related, their summation is also going to be periodic. And the minimum common form that you find, which is common in all of these, the basic frequency, angular frequency, is pi by 3.
Moving to question number 6. The question says, let xt be a continuous time complex exponential signal xt. So complex exponential is of the form e to the power j omega naught t, which has a fundamental frequency of omega naught and the fundamental period 2 pi by omega naught, that is t naught. Now consider a discrete time signal obtained by taking equally spaced samples of xt, that is xn is xnt, which is equal to e to the power j omega nt. We need to show that xn is periodic if and only if t upon t naught is a rational number, that is, if and only if some multiple of the sampling interval exactly equals a multiple of the period xt. Now, what this exactly means, let us see. So the question says that we've got a signal xt, which is a complex exponential, e to the power j omega naught t, where omega naught is the fundamental frequency of this signal, right? Now, a uniform sampling is performed on this signal. What do we mean by that? Say, let xt be an input, and there is, say, a switch that closes every ts seconds. Let Ts be the sampling interval, means interval after which this switch closes, or the interval after which a sample is recorded. What would happen? Such a system will give us an output only when T is equal to Ts, then T is equal to 2Ts, 3Ts, and so on, right? That means we can write that such a sampled version is something of the form x of nTs, where n can be 0 or plus minus 1, plus minus 2, and so on. So, for example, if xt was a signal like this along time axis, then your x of nts looks something like this. This is how x of nts would look like. Now, if we were to eliminate ts, right, and simply write it as, express it as a discrete time signal, we could call it x of n, and this is how a continuous time signal now becomes discrete time signal, right? From xt, we noted equally spaced samples, and then if sampling period was independent, right, if it was immaterial, we could identify the signal completely in terms of its sample number, and we started calling it xn. Now the question here is that if the signal is a complex exponential like this, and sampling is done at intervals say ts, we need to show that the sampled version, this xn, we know that xt is periodic, right? There is no doubt about it, because no matter what is the value of omega naught, xt will always be periodic. But xn, the discrete time sampled version, may or may not be periodic. Right? So we need to show in this question that if ts upon t naught being 2 pi by omega naught, that is the time period, right? Omega naught is given, so t naught is the time period, fundamental time period. We need to show that ts upon t naught needs to be of the form some k by m, right? That means some m times ts should be equal to k times t naught. That is what the question says. right, for xn to be periodic. So let us see how to go about this. Okay. Now, for xn to be periodic, what does it mean? It means that xn should be equal to some xn plus capital N, if n is the period, right? So we already know what is xn. We know what is xt. So xn can be written as x of nts. So just plugging in xt here. So this becomes e to the power j omega. Instead of t, we will have only nts, right? So this is a function. Ts, omega, these are omega naught, these are known, right? So the only variable is n. So I can say that this is xn, e to the power j omega naught ts n. So if this is xn, how do I rewrite this equation? So this means that for xn to be periodic, e to the power j omega naught nts should be equal to e to the power j omega naught n plus capital Nts. Remember what is Ts? Ts is the sampling interval. Let us open this bracket. This becomes e to the power j omega naught Nts into e to the power j omega naught capital Nts. Now, this and this can get cancelled, and therefore you would get e to the power j omega naught capital Nts should be equal to 1. This means that this exponent should be equal to some multiple of 2 pi. So I'll continue here. So omega naught capital Nts should be equal to 2 pi k, for example. Now, what is omega naught? Omega naught is 2 pi by t naught into n into ts is equal to 2 pi k. 2 pi and 2 pi gets cancelled, and we can say that ts upon t naught should be of the form k by capital N. Now, in the minimum form, some minimum value of k, whatever is in the denominator, would be the time period, fundamental time period. So this condition should be met while sampling a continuous time signal to ensure that the sampled signal is also periodic. This also means that n times the sampling interval should be equal to k times the fundamental period. That means some multiple of t naught should also be equal to some other multiple, some finite multiple of sampling interval. All right. Thank you.